Hi guys, here's a little tutorial showing you how I solved each of the problems in the practice set, so you can follow along step by step if you need to. First step for number 2 is we need to figure out which formula to use, and to do that we have to decide, is this potential or kinetic energy that this baby carriage has? Well, it says that the baby carriage is sitting at the top of a hill, so it's not moving, so that must be potential energy. So we're going to use the potential energy formula. And the potential energy formula, as written on the sheet that I gave you, on the first sheet, says, it has it all written out, mass times gravitational acceleration, it gives you that number, 9.8 meters per second squared, times height. All of that's a big mess to fit in this box, so I'm going to abbreviate mass with an M, acceleration, gravitational acceleration as G, and height as H. And that's the abbreviated form of this formula. So now all I have to do in the next step, and I'm going to leave out the P equals just because writing in the iPad is hard to fit it into these little boxes. I'm going to fill in the mass, which is given to me in the problem as 52 kilograms. So we're going to multiply 52 kilograms. It's important to include the units here. It says with units. I would take off points if you just wrote 52. Gravitational acceleration is 9.8, and it has units also of meters per second squared. And the height, which is given to you in the problem, of 21. So you'll notice that you have to know the gravitational acceleration is 9.8. It tells you that on the formula sheet, but you have to know what that is. Okay, so now I'm just going to plug all these numbers into my calculator. Some students get a little bit confused by this squared in the units. A lot of times students feel like if there's a squared in the units that they should square the number, but that's not true. Just because the units that go with a number have a squared in it does not mean that you're going to square anything when you put it into a formula. That number has already been squared in the creation of the number. So you're only going to square something if that squared sign is outside of the parentheses, if it's not part of the units, which we'll see in another problem in a little bit. So I'm just plugging 52 times 9.8 times 21 into my calculator. And that comes back with this large number, 10701.6. Now some of you might at this point go ahead and do your rounding and add your units if you're particularly fast at this, and that's okay. You can do that in this step. I wouldn't take off points. It's just that I like to break it down into each individual step for students who need to go more slowly. So if you do need to go more slowly, I've given you a place where you can now take that number and round it here below. And this is a little bit tricky because this involves that weird rule where sometimes zeros count and sometimes they don't. What we want to do is we want to make sure that our answer doesn't have any more numbers in it than our beginning numbers started with, because we had tools that could measure out 2 places in each of our measuring devices, right? This one measured out 2 digits, this one measured out 2 digits, and this one measured out 2 digits. So our answer, when we calculate all those measurements times each other, shouldn't be more precise. It shouldn't go out any further than 2 digits. The problem we run into is if we just rounded this to 2 digits, which would be the first 2 digits, well then we would get 11, because 10, the next number is a 7, so we would round that 0 to a 1. So we can't just write 11, because that's way too small since we started with 10,701.6. So what's the nearest thing we can round to? Well, it's 11,000. The zeros that we're going to put in, those 3 zeros there, are placeholding zeros. They're replacing all the numbers that we really didn't know that we had a 7, a 0, and a 1 here. Those just showed up because of our calculation, but we don't really know what goes in those places. So we can't really say that we measured out to those places. We're just going to put placeholding zeros instead of them. So that little rounding step sometimes bothers people. And I get that. That's a tough step. So this is where it becomes really important when you're taking a quiz on this, that you write out all these steps, because this way, if you mess up the rounding step, you're not going to lose points for anything else, because you'll get credit for having written your calculator answer. And then no matter what mistake you made with your rounding, if you put the right units, you're going to get credit for that. So, you know, if the rounding's bothering you, make sure you're not losing points on top of not knowing how to round by just not filling in all the spaces. Okay, so now we have to put the units on. And the units for energy are joules, lowercase j. And that's it. We're done with that problem. So this baby carriage sitting at the top of a hill has 11,000 joules of energy just sitting there. Let's do the next problem. Okay, in this one we have a car that's traveling, so we know it's moving. So this is going to be kinetic energy this time. And the formula for kinetic energy is 1/2 the mass times the velocity squared. This time we're going to be squaring our velocity. So we are going to have to square a number to do our calculations. So when we plug in our information here, we're going to get 1/2 times the mass, which is right here, 1120 kilograms, times our velocity squared. So I'm going to put the units meters per second here, end my parentheses, and now here comes the squared. That's what's telling me I'm going to square that number. Now, you guys have those scientific calculators where you could probably just put all these numbers in exactly as you see them here. And as long as you put the parentheses in, your calculator will know what order to do the operations in. But if you have an old-fashioned calculator that's really just an adding machine like mine, then you have to actually know what order to do everything in, which means that you have to first take 40 and multiply that times itself, and that gives you 1600. And then multiply 1600 times 1120, and that gives you 1792000, and divide that by 2, because multiplying by 1/2 is the same as dividing by 2. So when I do all of that, I get 896000. Let me just check that against my original answer key. Yep, that's what I got. Okay, and now I need to round. So I'm going to go back to my original numbers and look at them, and I have 3 digits rather in the first number, but only 1 in the second number, because remember the 0 at the end is a placeholding 0, it doesn't count. So I can only have 1 digit, which is kind of annoying when you get a big number like this. It doesn't feel right to make 1 digit, but that's what you got to do. So you got to look at your 8 and say, do I leave it as an 8 or do I make it a 9? And since it's followed by a 9, it's going to be a 9. Then you have to say to yourself, hey, I can't just leave this as a 9, I've got to put zeros in there to hold the place of the other numbers that I took out. So that's your rounded number. And all of these problems, the units are going to be joules because it's energy. Okay, let's move on to the next problem. Okay, so in this problem, I made a mistake, and this might have messed some of you up, but I don't know, I'm thinking a lot of you probably just didn't even notice. It says it weighs 79 newtons. Newtons are units of not mass, but force, and weight is a force. Your weight is due to gravity. It's due to the force of gravity. So technically, 79 newtons could give you the mass, but you'd have to calculate the mass from that. So what I had meant to do was I had thought that I went through this worksheet carefully and changed all of the newtons to kilograms, but I didn't. I meant to, though. So if you could just do this problem with 79 kilograms, that would make it a lot easier for you, because I really don't want to get into the difference between mass and weight right now. Not that that's not important, but I just think that that's adding an extra complication that a lot of us don't need. So the best way to do this problem at this point for us is to change it from being a weight problem to being a mass problem. So I called it 79 kilograms when I did this problem. So if you somehow manage to figure out the correct way to convert weight to mass, that's fine. Don't worry about it. We can talk about that when I see you in class. All right, so the formula here is going to be potential energy, once again, because this object is just sitting there. Let me use the black pen. Hold on. Okay, so PE is mass, gravitational acceleration times height. So the mass here, I'm going to call that 79 kilograms. I apologize again for not changing the units. The gravitational acceleration, 9.8 meters per second squared. And the height is 20 meters above the ground. Now we're going to multiply all that out. And when I do that, I get 15,484. But I'm only allowed to have 1 digit because 20 meters has 1 digit. The 0 is a placeholder. So as annoying as this is, I'm actually going to wind up rounding up to 20,000. Now sometimes students get confused here and think they're going to round to 15,000, because of the 4 here next to the 5. But if you think about it, you're supposed to go to the next number, right? So 1 is the number we're going to round, and we have to decide do we want to keep 1 as a 1 or make it a 2. And to make that decision, we have to look at the number right next to it, which is a 5. And I know for some people this just feels weird, but it does round up because the number is a 5. So 20,000 is what we get. And again, this is going to be joules. All right, let's do the next one. Okay, once again, we have something that's just hanging out. It's a bell at the top of a tower, so this is going to be potential energy. Again, mass, gravitational acceleration, and height. The mass of this thing is 9,000 kilograms, pretty heavy bell. And then its acceleration due to gravity, 9.8 meters per second squared. And we're 45 meters above the ground. When I multiply all of that out, my calculator gives me 369,900. But once again, we're only allowed to have one digit, the 9. The other numbers in the kilograms there are placeholding zeros. So if I can only have one digit, I have to round this 3. Do I keep it as a 3 or do I make it a 4? Well, the number next to it is a 6, so that means I have to go up to 400,000. And you can see I picked these numbers on purpose so that this would keep happening, so that you guys maybe would hopefully get used to the fact that this rounding thing doesn't feel normal, but it is normal. You just have to get used to it. So a lot of energy in that bell. We do not want it to fall on us. Next problem. Okay, so this time we have a roller coaster, but be careful, it's a roller coaster sitting at the top of a hill, so it's not moving, which can be confusing, right? Sometimes students jump to conclusions that certain objects are always in motion. This is not in motion, this is just sitting there. So we're going to still be using potential energy. That's this formula, mgh, mass, gravitational acceleration, and height. When we plug these numbers in, we're going to get the mass is 1,500 kilograms. Gravity, 9.8 meters per second squared. I apologize for my handwriting. It's hard to write on the iPad. And then the height is 72 meters. When I multiply all of this out, oh, it's driving me crazy. I got to fix that 8. Sorry, guys, my OCD kicked in there. Had to fix that. Okay, so when you multiply that out, the 1,500 times the 9.8, times the 72, you're going to get this huge number, which I guess is 1,058,400. We have to round this. We get 2 digits because we have 2 in 1,500, 2 in 9.8, and 2 in 72. So I'm going to have to round this. Does it stay as a 0? Nope, it goes up to being a 1. So that's going to be 1,100,000. And again, that's joules. So even more powerful than our bell was. Definitely don't want this roller coaster hitting us. Even though it's not moving yet, it has a lot of potential for energy when it starts to move. Okay, let's take a look at the next one. Okay, in this one, they just flat out told us that we're dealing with kinetic energy, which is nice. So we have kinetic energy is equal to 1/2 the mass times the velocity squared. Our velocity and mass are given to us, so our mass is 3 kilograms. And our velocity, you had to recognize it. It's telling you it's rolling at 2 meters per second, which we write like this. And that 2 has to be squared. So remember, when you're doing this in your calculator, you either have to put it in with all the parentheses in the right place, or you have to do the steps for the calculator if you have the kind of calculator like I do. So in that case, since I have this calculator that doesn't, take parentheses and stuff like that, I had to first square 2. So I put this into my calculator, 2 times 2, which gives you 4. And then I multiplied that 4 that I got from doing this by the 3, which gives me 12. And then I divided by 1/2, or rather multiplied by 1/2, which is the same as dividing by 2, so that gave me 6. My original numbers only have one digit each, so that's good, so I don't have to round anything. And this is 6 joules. And that makes sense, right? So a ball that's rolling is not going, a 3 kilogram ball is not going to have as much energy as, say, a roller coaster, right? And we're rolling down a hill, not a mountain. So we're not going to pick up that much energy. All right, next problem. Okay, so this is actually one giant problem. You won't see anything this complicated on your quiz. This requires that you already be really comfortable with doing this, because I'm adding an extra layer of difficulty by putting a whole bunch of information in one place. Sometimes it can be helpful to just kind of make yourself a list when problems like this appear of what all the information is that you've been given. So you could make a list of, what is the mass of each car, and what is the velocity of each car, and stuff like that. And we can talk about that in class if that kind of problem solving will help you. We can certainly spend a little time on that on Thursday when I get back. But for right now, I think you should focus on just doing each part one step at a time. And that's kind of how I broke it down for you. So part A is basically asking you for the potential energy of both cars. And for them to have the same potential energy, they have to be at the same height above the ground and have the same mass. So even though I didn't tell you that they have the same mass, you kind of have to assume that. So they both have a mass of 0.1 kilogram. So the formula for potential energy is the mass times gravitational acceleration times the height. And like I said, the only way they could both have the same potential energy is if the mass and the height are the same. So we're going to give them both a mass of 0.1 kilograms. Gravitational constant, always the same here on Earth. We change planets, we'll have to change that number. And then the height, it was said, was 1 meter. So both of these cars are going to have this much potential energy because they have the same height above the ground and they have the same mass. So when we calculate this out, you're going to get 0.98. Now decimals freak people out. So when you see 0.98 and then you have to round to one digit, sometimes people go, I don't know what to do. What do I do here? Oh my gosh, right? Because the 9 has to round up to a 1. But you have to realize that when the 9 becomes a 1, that 1 moves to the left of the decimal, right? Because if you had 1.98, if this was your number, you'd know instinctively that you're going to round that to a 2, right? Because there's already a number there. Well, there's an imaginary 0 here, so we're basically rounding up to 1. That confuses a lot of people. So what are the units? Joules. So both cars have 1 joule of potential energy. Okay, let's do the next part. Okay, so in part B, we need to find the kinetic energy for car A. So for kinetic energy, we're going to use Ke equals 1/2 the mass times the velocity squared. And we know already that our mass for both cars was 0.1 kilogram. 0.1 kilogram. So what's the velocity of car A? So car A's velocity was 2.5 meters per second. And we have to square that number. So when we do our calculations, for me in my calculator, I'm going to do 2.5 times 2.5. And then I'm going to multiply that by 0.1. And then I'm going to multiply by 1/2 or divide by 2, which gives me an answer of 0.3125. And when I round that, I only get one digit, so I'm just going to round to 0.3. So the potential energy started as 1, but we only have 0.3 joules of energy by the time this car gets to the bottom of the hill. So a lot of energy was dissipated or lost as that car came down the track. Okay, let's do this for the other car. Okay, so again, kinetic energy, because we're looking for how the energy of the car once it starts to move. And car B has a mass also of 0.1 kilogram. But this time it has a velocity of 3.0 meters per second, and we have to square that. So when I square 3.0, I get 9. 9 times 0.1 is 0.9, and 0.9 divided by 2, or multiplied by a half, is actually 0.45. I'm allowed only one digit, so it's 0.5, and this will be 0.5 joules. So this car also lost energy, but not as much. So the last question down below is what we're going to want to answer next. Sorry about that. There we go. So group B's car lost only 0.5 joules of energy, and I got that the same way. I started with 1 joule of potential energy. We lost 0.5 joules. I could tell because 0.5 joules is what we were left with, and that's how that adds up. And then I wrote this explanation down at the bottom. See if you can follow my logic. I'll try and make it so you can read it. Since both cars started at the same height and had the same mass, and both were under only the influence of gravity, it appears car A must have had more friction and or air resistance due to its shape. Because car A dissipated more energy, right? And so the only explanation for that, if they're the same height above the ground and they have the same mass and we didn't push either car, the only real explanation for that is somehow more energy was converted to heat and sound for car A. And how would that happen? Well, probably because car A's shape either had more air resistance pushing back on it, so there was more rubbing between the air and the car, which would result in a lot of energy being converted to heat and sound, or it could have been something to do with the friction between the wheels and the ramp itself. So you saw a lot of this with your balloon cars, right? That the design of your car affected the amount of friction that the car experienced. Now we're just looking at it from the viewpoint of energy instead of the viewpoint of force. And remember, this energy isn't gone from the universe, it's just converted from one type to another. So it's not useful to the car anymore, but that energy is still out there. It warms up the air and it hits your ear as sound. So you can definitely hear a car rolling down a ramp for sure. Okay, and that's it for these practice problems. Don't worry if you're still having difficulty. We'll certainly have more opportunities to practice before the quiz, and I'll see you guys in class.